Welcome to the Formal Models course. In this course, you will learn about various kinds of formalisms that can help you to get computing systems right, to verify that they are correct, or to find bugs. With these formalisms, you can concisely specify the behavior of the software or of the hardware you are developing as formal models. A special focus is set on concurrent systems, for which it is very challenging to get them right. After this course, you should be able to read formal models, and you should also be able to come up with them to specify your software or your hardware. The first formal modeling language we will consider are Finite Automata. Most likely you have already heard about Finite Automata, maybe in the digital design course or in the complexity course or maybe in compiler construction. In all of these areas of computer science, Finite Automata play a very important role for describing, for example, hardware systems, for describing programming languages and pattern matching, and also they provide quite comprehensive model of computation for defining systems with states and their behavior and certain properties. In the context of formal verification, they are also a core concept, and as we will see, they are not only important as a formal modeling language on their own, but they also serve as the basis for many other formalisms. So we will find the concepts we have here in the Finite Automata also in other formalisms as well. And in contrast to other application fields of Finite Automata, where they are used for describing, for example, languages and or check if some patterns match or can be found in an input string. In the context of formal verification, we use them for specifying event streams or sequences of actions. So the question we are interested in is given a sequence of actions, a trace produced by a program, is this conforming to the specification? And so here we are dealing with events or actions. And Finite Automata are also used to specify protocols, so the interactions between server and clients, for example, and with this it can be formalized how a client, for example, has to how a client has to contact a server in order to log into some system. Here I have a very simple example which models a door. We have two states. One state is opened and the other state is closed. So a door can be open or it can be closed. In the beginning, we have an initial state that the door is opened. So this arrow here indicates that this is the state in the beginning of the execution of the system. And there are two actions. One action is close. And when I'm in state opened, I may execute the action close. Then the door switches to state closed, and there the action open can be executed, and we switch to state opened. So this is a very simple model, and what we can see here is that we cannot execute close when the door is already closed. This is all expressed by this model, for example. What we also here is what we have here also is a situation where we have a system that does never stop, so we do not have any final state where the system terminates, but this is a system that is executing forever as long as the system exists, what makes sense with respect to a door, because it will not shut down. And this we also have in the context of computing systems. So many reactive systems do not terminate, but they should run until they are thrown away. But coming back to the concept of Finite Automaton, what we have here is in principle a virtual device for processing strings, and roughly speaking, there are two kinds of finite automata. There are those which can be used for checking if a string has a certain form, so it is accepting or rejecting a string. And this we would use in the context of formal verification to see if a sequence of action fits with the specification. And the other type that we have are so-called transducers, which also produce some outputs. We will also consider this kind of finite automaton in this course, but not in this lecture, but in the next lecture. And yeah, as I said, finite automata are the basis for many other formal modeling languages that we will see. And nowadays they are very widely used as some kind of semi-formal modeling language in the context of the unified modeling language. There they form the basis of UML state machines, which have many more concepts than the simple language we will introduce today. But in principle, a UML state machine is a very advanced kind of finite automaton. Yeah, and now we will introduce the language of finite automaton formally. But before we do so, we will have a short look what formal finite automata actually describe, and what they describe are formal languages. And here I have to give you some definitions. For introducing a formal language, we first have to introduce an alphabet. This is very similar to a natural language. We also have an alphabet we are talking about. And an alphabet, we call it usually sigma, is simply a finite sequence, a finite set of symbols. Yeah? So we have a set of symbols that we use to form words. And a word over an alphabet sigma is simply a finite sequence of a certain size. Let's call the size n. So if we have a word of size n, then we have a sequence of n symbols, where those n symbols come from the alphabet sigma. There's one special case. We can also have the empty word or the empty string, and this is a sequence of size 0, and this special word we denote by the symbol epsilon. Then we are also interested in collecting the set of all words that can be built from an alphabet, and this set of all words we denote by sigma star. And what is important here is that even if the alphabet is finite, the set of all words is usually infinite. Yeah? Because say we just have one letter, A, then we can build the empty word, the word containing just A, then the word containing AA, the word containing AAAA, and so on. Yeah? So we have an infinite amount of words in this sigma star. And we are not usually interested in the set of all words, but in a subset. And the subset we are interested in is called a formal language over sigma. Yeah? And here I have some examples. Assume we have an alphabet that consists of the symbols A and B. Then sigma star is epsilon, A, B, AA, AB, BA, BB, and so on. So we have an infinite amount of words. And then here I have some examples of formal languages over sigma, like the empty language, which does not contain anything. And this language has not to be confused with the language that contains the empty word. Yeah? So the language L1 does not contain any word, so the number of words we have here is 0, while here we have one word in the language, and this is the empty word. Yeah? Then here we have the language consisting of the two symbols A and B, which are the only two words we have. So we have one word which is just consisting of A, and we have the other word just consisting of B. And lastly, we have the language L4, which is exactly the example I mentioned before. It is the language that contains all words which can be built from letter A. So the empty word A, and so on. What is important is that an element of the alphabet is not necessarily one symbol of our alphabet as we have it here. If we go back to our example from the first slide, then the alphabet of this automaton are the symbols close and the symbols open. So close is one element of the alphabet and open is one element of the alphabet. And valid words described by this automaton we have here are close, open, close, open, close, open. What we now here have is we cannot construct finite words, but in the following we will talk about only finite words with because we are talking about automata which have final states, which allows us to decide if a word of length n is accepted or not. Okay, so now let's have a look how a finite automaton is specified, and we have here the mathematical definition. A finite automaton is a tuple that consists of several elements, 5 elements. We have S, the set of states. Then we have I, the set of initial states, the starting states. I is a subset of S. Yeah, note that we do not require to have exactly one initial state, but our definition allows to have 0 initial states, because the subset is also the empty set is also a subset of S, and we can have multiple initial states. So even every state could be an initial state. We will discuss the consequences a bit later in detail. Then we have the input alphabet sigma, and we have the transition relation, which tells us how to connect the state. And the transition relation is a set of triples built from a state, an element of the alphabet, and another state. So we have the source state, the symbol of the transition, and the target state. We can write it as triple, as we have it here. S prime is an element of the transition relation. But alternatively, we also write it with a small arrow. So we write on the left the source state, then we write an arrow with the symbol above, and on the right we write the target state. Those two notations are equivalent, and it doesn't matter which one of them you use. And in textbook you will also find many other definitions as well. Maybe you noticed that we have a transition relation and not a transition function, which is also very common to define a finite automaton. What is the effect? This we will also discuss a bit later, but to make it short, is that with having a transition relation, we are allowed to have to model the situation that we have one one source state, And then we have two outgoing edges from S, from the start state S, which are both labeled with the same symbol, but which result in which end up in a different target state. Yeah, so what we include here is non-determinism, and we could have multiple transitions labeled with the same symbol, starting from the same starting state but ending up in different target states. But this we will also see a bit later. Yeah, and the last component are the set of final states, and this is also a subset of states. Here we have the graphical representation, which is often very convenient to use. This is also similar to the notation we have already seen before. We have states which are denoted by a circle and the label of the state inside. Initial state we mark with an incoming edge without some source. Then final states are denoted by this double circle, and transitions are simply the two states and their connection, and the connection is an arrow with the direction and the label. So we have a transition from S1 to S2 that is labeled with an A. Yeah? So this is how a finite automaton can graphically be represented. And here I have a very small example. Here is the graphical specification of an automaton. We have an initial state as 0. Maybe let's start at the beginning. So we have states as 0, S1, and S2. This is written down here. Then we have one initial state as 0, which is here, and which is also marked by this arrow, which has no source. Then we have the alphabet, which is AB. Yeah? No other symbols are used here. And then we have the transition. The transitions here, the transition relation. In this case, there is no non-determinism, so it's always clear what is the next state if we know the symbol. From S0 with an A we can go to S1, from S1 we can go to S2 with a B, and from S2 with an A or with an B we can go to S2. This I denoted here with a star, which is a placeholder for saying any element of the alphabet can be plugged in here. Yeah, and finally we have one final state, which is S2, and this is denoted by this double circle which we have here. Now that we have introduced this concept of finite automata, we also want to use it for something, and we want to use it for describing formal languages. For this purpose, we have to introduce the definition that says what it means if an automaton accepts a word. And this is the definition we have here on the slides. Given a finite automaton A that is defined over this 5-tuple as we have it introduced it above, we say that A accepts a word omega of length n, where omega consists of symbols from sigma. We say that A accepts such a word if there exists sequence of n+1 states and n symbols, such that we can go from a state S0 with symbol A1, which is the first symbol of omega of the word, to a state S1, and then with symbol A2 we go to the next state S2, and so on, until we end up with the last symbol from omega in state n. And very important, S0 is an initial state of A, and Sn is a final state of n of A. And if we have such a sequence, then we say that the word omega is accepted by automaton A. There are some special cases. If the length of the word is 0, if n is 0, then omega is the empty word, the empty string. And now we can say what is the language that is described by a finite automaton A, and the language LA of an automaton, finite automaton A, is the set of words that are accepted by A. Let's look at an example. We have this automaton we have seen before. We start in state S0, then we read an A and end up in state S1, then next we read a B, then we end up in state S2, which is also a final state, and then we can have an arbitrary sequence of A's and B's, but we still remain in state S2. So what we are describing with this automaton is the set of all words that start with the prefix AB. Hence, the string AB is in the language of A, the string AB is in the language of A, the string ABA, so where we have some A's afterwards, is in the language of A, and so on. All strings that start with AB are in the language of A, because we first read an A, then we read a B, and then we are in the final state when we start from initial state S0. However, epsilon is not in the language of A, because S0, the only initial state, is not a final state, and strings like BAAB are also not in the language, because, for example, this string starts with a B, but here we say the first letter, the first symbol, has to be an A. Hence, the string BAAB is not in the language of A. Obviously, it has some impact on the language. An automaton describes how initial states and final states are selected from the set of states, and there are some special cases which I would like to quickly show you, and which are possible according to the definition of finite automaton as we have introduced it before. So first of all, it could happen, or the definition allows that there are no initial states, as we have it here. In this automaton A, we have two states which are for some reason above final states, but there is no initial state. This means that we have a language that is empty, described by this automaton, and also here in this automaton B, no word can be accepted. Here we have an initial state, but there are no final states, and therefore no word can be accepted. So the languages described by A and B are both empty. Yeah, then something I would like to mention, because this causes often some confusion, is the automaton which just accepts the empty words. This looks like this. We have an initial state, and this initial state is the only state, and it's at the same time the final state. The language described by this automaton C is the language containing epsilon, and this is not the same as we have in the case of automata A and B. So the language of C is not empty. It contains one element. It contains the element epsilon, and this is different to the empty set that we have for the language of A and for the language of B. Yeah, so there is a difference if I have nothing in my language, or if I have this one element which is the empty string in my language. Yeah, and then some other properties which are very important for the characteristics of a finite automaton are summarized on this slide. Before I tell you these properties, we have to introduce this A successor set. So if we have a finite automaton, then by this S arrow A, we denote the set of A successors of a state S, which is defined as follows. In this set, we collect all the target states which can be reached from S with an A. Yeah, we said we have a transition relation, meaning that there can be multiple successor states that are reachable via an A. And if we collect all the states that are reachable via an A from S, we write it down as S arrow A and no target state. Yeah? And now we introduce these two important notions of completeness and determinism. We call a finite automaton A complete if and only if A has at least one initial state. So the set of initial states is larger than 0. There is at least one. There can also be multiple. And we require that for each element of the alphabet and for each state of the state, this A successor relation is larger than 0. This means that for each element of the alphabet, each state has an outgoing edge with this symbol from the alphabet. Yeah, so it cannot happen that we are in a current state S and there is no outgoing edge labeled with a symbol from the alphabet. And we call a finite automaton deterministic if and only if A has at most one initial state, so it can have 0 initial states, but it can also have one initial state, but it cannot have multiple initial states, so we exactly know where to begin. And for each symbol and each state, there is at most one transition labeled with the symbol. So it cannot happen that we have this kind of indeterminism, which is possible by the transition relation. And if we always know where to proceed next, then we call a finite automaton deterministic. Yeah, often in the literature, these deterministic automata are introduced separately from the non-deterministic automata by giving a transition function here and not a transition relation. So that it's made explicit that the next state, if defined, is uniquely determined. But we have combined this all in one concept, and we handle the deterministic finite automaton as a special case of the non-deterministic automaton. And now, if we combine these two properties, we get the following proposition, which directly follows from the definitions. A finite automaton is deterministic and complete if and only if it has exactly one initial state, and for each symbol and each state there is exactly one transition possible. Okay, let's look at some example. For this I need my writing space. Yeah, here I want to show you some artificial examples just to illustrate the concept of determinism and completeness. So assume we have a state of set S with S0 and S1, and we have an alphabet sigma which is consisting of the symbols A and B. Yeah, so now we want to construct deterministic and complete automata. So the first one is non-deterministic and non-complete. Because we have two initial states, therefore it's non-deterministic, and it's not complete because we just do an A here and no B here, or here we do even nothing. Yeah, then let's do a one that is deterministic. So for example, this one, it's deterministic, but it's not complete because here no B transition is done. So if I'm in state S0, I cannot proceed with a B. Then let's construct something that is not deterministic but complete. For example, if we do something like this, then this is not deterministic, non-deterministic, but complete. We have at least one initial state, and in each state we can proceed with each letter from the alphabet. And finally, let's do something that is deterministic and complete. Say we have B here, with an A we go here, S1, and here we do A, B. Yeah? This one is deterministic and complete. We do not say anything about the final state, about the accepting state. It's just about the properties of the transition relation as well as the number of the initial state. So this one is deterministic and complete. And we usually want to have this kind of automata, and later on we will see how we can transform a non-deterministic, non-complete automatic into one that accepts the same language but which is deterministic and complete. For describing a system, it's often more natural to use a non-deterministic or non-complete finite automaton, but there are techniques which require these properties, and then if we do not have them, we cannot apply them. Hence, it's then necessary to transform the non-deterministic, non-complete automaton to a deterministic and complete automaton which accepts the same language as the original automaton. And the question is this always possible? And as we will see, the answer is yes. By the construction of the power automaton, we can always construct an automaton which accepts the same language as the original automaton and which is deterministic and complete. And now let's have a look how this power automaton construction works. So we have given an automaton A as before, and this automaton is not necessarily deterministic nor complete. And the power automaton is constructed as follows. So we construct an automaton which has different set of states and hence different initial and final states, a different transition relation, but it has the same alphabet as the original automaton. And now let's have a look how the other components are defined. The set of states is now the power set of the original set of states. So the states of the power automaton are subsets of the states of the original automaton. We combine states that have somehow similar properties into one state, and hence we have sets of states as states. Then what are the initial states? The initials, so not the initial states, but only one initial state because it's deterministic and complete. So we have exactly one initial state, and this initial state is simply the set containing all the initial states of the original automaton. Yeah? This is also a set of the power automaton. Then we have the final states, and the final states are those sets of states which contain a final state of the original automaton, so where the intersection is non-empty. When we take a final state from from the power automaton and intersect it with the final state set of the original automaton, and the intersection is now empty, then it's a final state in the power automaton. And finally, we have to define a transition relation of the power automaton, which is in fact now a transition function. If we have a state S prime that contains some states of the original automaton, then from this state S prime with symbol A, we target a state S double prime, where S double prime is simply the union of all the states that are reachable from a state from S prime with A. Yeah, so we collect all the states that are reachable with an A. Okay, so let's have a look at an example, then it should become more clear how this construction works. We are given this automaton A, which is obviously not deterministic because it has two initial states, and it's also not complete because from the state S1 we can neither proceed with A or B. And we now want to construct the power automaton of this automaton A, so we want to construct PA. So first we collect the initial states, which are S0, S1, and combine them into one state. I've read this like this, so I do not add set parentheses or commas. I just write this included sets here as a label. Okay, so we have now state S0 and S1 in the initial state. Next, we have to consider where we can go from this state with an A and where we can go with an B. With an A, we can go from S0 to S0 and we can go to S1. So with an A, we stay in this state. Then where can we go with a B? There is only one option. So with a B, we go to S0. With a B, and now we check how we can proceed from S0. Yeah, with an A, from S0 we can go to S0, or we can go to S1. So we do an edge which goes back here. And with a B, we stay simply in S0. And that's it. So there are no further states that have to be considered. What I do here is an on-the-fly construction, so I include only those states that are really necessary for the construction and not all states, because otherwise we would have these exponential blow-ups, and I mean in the worst case we have it, but we can hope that we do not have it for the automaton we are considering. Okay, so one thing is missing, and the thing that is missing are the final states. And for the final states, we have to check what are the states here that contain the final state S1, and there's only one, and this is this here, and this is the power automaton of A. Now we can check if it's accepting the same language. Yes, the power automaton accepts also the empty word, and and every word that is accepted has to end with an A. Here I forgot to add the label B. Yeah. So we can have an arbitrary combinations of A and B, but in order to get to the final state, we have to have an A at the end. Yeah, and this automaton has now exactly one initial state, and from each of the two states we can do an A and we can do a B to one successor state. Therefore it's deterministic and complete. Now let's look at a larger example. This automaton here is also not deterministic and complete. It's not deterministic because here we have two B's that are outgoing, and it's not complete for many reasons. For example, here is no B. Okay, so how do we proceed here? Here we have only one initial state, so we start with S0. And from S0 with an A, we can go to S1, or we go to S1. Okay, but there is now no way to do a B specified here from S0, and what we do now is we go to the state with the empty set, which is also a subset that is contained in the power set of S, and this can be seen as some kind of an error state, and if we're there, we stay there forever. Yeah, so no matter if we have an A or a B in this state, we stay in this state. Okay, then what do we do from S1? From S1 we cannot proceed with an A, so we go to the error state with an A, and with a B we have two choices. We go to S2 or to S3, and in the power automaton we combine S2 and S3. This is where we proceed with a B. Now if we are in S2, S3 and we have a B, then with this B we stay in S2, with this B we go to S3, and there is no other way how to proceed with a B. So we have this loop here with a B. And what happens if we get an A? With an A we go to S2 here, or we go to S4 here. So with an A we go to state S2, S4. Okay, and how do we proceed from here? From S4 we cannot do anything, but from S2 with an A we go to state S2, and with a B we go to S2, S3, and this we already have here, so we do not introduce it again, but we reuse it, and then we are done with this state S2, S4. And now we have to handle S2. With a B we go to S2, S3 again, and with an A we stay in S2. Okay, and now final states. Here the only final state is S4, so we have to check in which states of this automaton we have S4, and we have it here. So this state is the only final state in the power automaton. Okay, yeah, and this is what we get when we want to have the power automaton of this automaton. Let's have a quick look. What is the language this automaton accepts? So it reads A, B, A as one word here. Let's see if we also have just some short plausibility check. A, B, A is also accepted here. If we have A, B, then we can have an arbitrary sequence of A and B, and then we end with B and A. So here we have this A, B. Then we can have an arbitrary sequence of A's and B's. Yeah, and we also end up with B, because here in this state we only enter with a B and end up with an A. So looks quite plausible what we have here. Yeah, so this was another example for the power automaton construction. And here we already have an example where we need a deterministic and complete automaton in order to make a technique work. And this is for getting an automaton that describes the complement language of a language that is described by an automaton. What is the complement language? Yeah, we said sigma star is the set of all words, and if an automaton describes a language LA, then the complement of this language is simply sigma star without the words that are included in the language. So we have simply the words that can be constructed via this alphabet, but which are not included in the language, and this gives us the complement language. Yeah, and sometimes we need to talk about the negation. Sometimes it's easier for solving certain verification problems, for example, and for this we need a way to get an automaton that describes the complement language and not the original language. And for this purpose we have the complement automaton construction. So given an automaton A defined as usual, the complement automaton of A is simply the automaton we obtain when we take the same components as we have in the original automaton, but we exchange the finite state by the complement. Yeah, so we take S and remove all final states, and this gives us the complement automaton. So what we do in the graphical representation is we exchange simply all final and non-final states. The final states become non-final states, so we remove the second circle, and the non-final state become final states by adding the second circle. And now we have the following theorem. The complement automaton CA of a deterministic and complete finite automaton accepts the complement language of A. Yeah, so here it's really important that the automaton, the original automaton, is deterministic and complete. And if it has these two properties, then we can be sure that if we simply exchange final and non-final states, we obtain an automaton that describes the complement language. Let's have a look at an example. Here we have this big automaton from before. This was the automaton we obtained by the power automaton construction, and so we know that it's deterministic and complete by construction, and here we have one final state, and what we do now is we simply make this final state a non-final state, and the other states become final states. In particular, also this state with the empty set, which was some kind of an error state, becomes also a final state, because obviously these words which are not accepted by the original automaton are now accepted by the complement automaton and are obviously in the complement language. Yeah? So we said that here in this automaton we have the words that start with AB and end with BA. So we have at least ABA in the language as the smallest words, but there are other words as well. And now we can check if we can have this word ABA in the complement automaton. So if we have A, we have B, and we have A, then we deterministically go to this state S2, S4, but this is now not a final state, so it cannot be accepted. On the other hand, we now accept the empty word, for example. We accept the word which just contains the letter B or just consists of the letter A. We consider this language contains all words that have an arbitrary sequence of A's and B's after letter B, and so on. Yeah, obviously all words which are not in automaton A's language are now in the complement language. Yeah, and now I will also give you some intuition why it's important that the original automaton is deterministic and complete, but for this I will switch to my writing space. Assume we have the following automaton. We have a state S0 as an initial state, and with an A we go to S1, with another A we go to S2, which is a final state, and here from S0 we also go to S4, which is also a final state. So sigma is just containing letter A. It's Problem A. This automaton and the language of A are two words. We have A and AA. These are the two words which are accepted by A. Okay, so if we now do the complement automaton of A, what do we get? We get S0 becomes a final state. Then with an A we go to S1, which becomes a final state, and S2 is a non-final state, and also S4 is a non-final state. Okay, and this original automaton was neither deterministic nor complete. And we have now the first problem that in the language of the complement automaton, we have epsilon, this is fine, but suddenly we also have A, and this A is here and here, and so we have a clash. It cannot be that an element is in the language and in the complement language, and this is because of the indeterminism we encountered this problem. The next problem is that because this automaton is not complete, we lose the possibility to construct words of length larger than 1 actually, because here epsilon is accepted, A is accepted, but nothing else. So already what we have here is the language. So in the language we have just epsilon and A, but there are many words, more words which could be constructed from symbol A. So what about AAA? This we cannot have because we cannot proceed from S2 and we cannot proceed from S4, and for this reason we have not enough elements in our language. Okay, so this was the example I wanted to show you. There's a problem with the power automaton construction, or let's better say there is a practical limitation when using the power automaton construction. The power set is exponential in the size of the original set, so if the set size is n, then the power set has 2 to the power of n elements. And in the worst case, all of these elements are used in the power automaton, and therefore we have an exponential blow-up. What we have seen was this on-the-fly construction, so we considered only those states that were reachable from an initial state, and the hope is that the power automaton that is constructed from an automaton does not need all the states or needs only a few states, but it can be shown that in worst case all states are needed. There are cases. And this is a real practical limitation because then the power automaton is too big and cannot be really used. And there is something what I would like to show you next, which is a very nice trick. And here the idea is to replace non-determinism with an oracle. So to make the original non-deterministic automaton formally deterministic by encoding the non-determinism on in the labels of the transition. And how does this work? How can we imagine this kind of construction? So we have again given a finite automaton A, and the oracle automaton of A extends the alphabet. So the alphabet is now a set of pairs where the first component is sigma, so an element of the original alphabet, and the second component is a state. And when we change the alphabet, we also have to change the transition relation, but everything else remains as in the original automaton, and now we have to say how we change the transition relation. So if an alphabet is now this pair, then an element of the transition relation has now this form. So we have a source state and a target state and an element from the alphabet, and the first component is simply the symbol we also had in the transition of the original automaton, and the second component here is now the target state. So we encode the target state in the label of the transition, and by this we formally get a deterministic automaton. And if we now have a projection function, meaning that when we simply remove the second component of the pair by this projection function and just keep this first component, when we analyze a word, for example, then we obtain the language of the original automaton. And if we have exactly one or no initial state, then the oracle automaton of an automaton A is deterministic. If there are multiple initial states, this construction doesn't help because it cannot do anything about the initial states. Yeah? But it can remove a non-determinism from the transition relation. Okay, so I will show you an example how this construction works, and it's really simple. So assume we are now given this automaton we have here on the left hand side. Let's call this automaton A, and we want to build the oracle construction of it. So we want to construct oracle of A. I have prepared a copy of it and I will modify it to get the oracle automaton of A. For the moment, ignore that there are two initial states. We'll discuss this at the end. We will just apply the construction now. And what we simply do is we extend the labels of the transition and add the target state. So here I add B as 1, then I have A as 1, B as 1 here, then we have B as 4 here, then we have A as 4 here, we have B as 4 here, then here we have B as 4 as well, here we have A as 4, here we have A as 2, then here we have A as 3 and B as 3, here we have B as 2, and here we have B as 1. So I simply added the target states. And if we now look at the transitions, we see that we have no state anymore which has two transitions that are labeled with the same symbol of the alphabet. Yeah? With this respect, it's now deterministic. The problem is that this one is still not deterministic because we have the two initial states, and about those two initial states we cannot do anything. If there had been only one, as in the example on the slides, then there is not a problem and we obtain a deterministic automaton. Here we have the problem that because of the two initial states, the automaton is not deterministic, although we fixed the transitions respectively. Yeah, there is another issue. If we now look at the alphabet, this is now very large. So we have A as 0, A as 1, A as 2, and so on. Yeah, and the same for B. We have B as 0, B as 1, and so on. And while this automaton, the A automaton, was complete, so here we have AP, here we have AP, here we have AP, here for S2 we have A and B outgoing, and for S3 we also have S, A and B, and we have initial states. While this automaton was complete, the new Oracle construction is by far not complete, because we have many transitions that are not included, or many labels are not included for each state. Therefore we lose the property of completeness. But we will fix this with the next construction, with the Oracle automaton. But before we do so, I would like to quickly show you how words look like. So for the empty word, it's still the empty word, but let's take another example. For example, A, B is a member of the language of A. Okay, and now how would the same word look in the Oracle automaton? Here we have the now AS1, AS1 again, and then we have BS4, which is in the language of Oracle of A. Yeah? And if we project on the first components of the symbols, then we get AAP. Yeah? So we have this projection function P1 and P1 of AS1, AS1 and BS4 gives us A, B. Yeah? And so in principle we formally, with respect from the transition, we now have a deterministic automaton, besides the fact that it didn't consider the initial states, but in order to decide where to go next, we kind of have to throw a dice and decide, or use an oracle in order to decide where to go next. But in principle, on the paper, this is now a deterministic automaton, and this might help when you have tools which, for example, want a deterministic automaton for solving some tasks. So as we have discussed in the previous example, the Oracle automaton of a complete automaton is usually not complete, and now we try to fix this by introducing an optimized variant of the Oracle automaton. And for this purpose, we first identify the maximum number of successors we have of all states and all symbols. So we somehow identify the degree of indeterminism we have in the automaton, and more formally we identify n, and from all states and all symbols we identify the maximum size of A successors for all symbols A of the alphabet. Yeah? So we look at the automaton and identify the state which has a maximal number of outgoing transitions labeled with a certain symbol. Yeah? And this gives us now the information we need in order to build the optimized Oracle automaton and say that n is this number which we identified. Then the Oracle automaton now has as alphabet not the state as a second component, but a number which is between 0 and n minus 1. And this means we just number the transitions, and then we can really use a dice in order to decide where to go next. Yeah, and for the transition relation, this means the following. So if we are in a state S, then with symbol A in the first component and I in the second component, where this is now a number between 0 and n minus 1, we go to a state Sj, if and only if. Now we have to identify what is this Sj, and this is one of the states we can reach from S with an A, and we give each of the states a number, and this number is m minus 1 at most. Yeah, we again start with 0, and we also know that m is smaller than n because n is the maximal number of an A successor, so m is smaller. And the only problem is that we could have now more, that n could be larger than the m, and for this we have to wrap around, and for this purpose we use the modulo. And if there are, so if we have fewer A successors, then maybe some transitions are labeled with two additional symbols. Yeah, and this is what the modulo does. In order, if we have, for example, n is free, n is free, and m is just 2, then we have a gap of 1, and we have one transition which is labeled with an I, with I0 and with I2. Okay, let's have a look at an example. So if we look at automaton A from before, then we first have to identify the n, yeah? And if we look at S0, then there are 3 B's outgoing. So this is already a very large number. But let's see if we find something larger. Here we have only one A, here we have one A, one B, here are 2 B's, here is one A, one B. Yeah, so 3 is indeed the n which we are considering, so n is 3. The maximum number of indeterminism, the maximum number of some successors is 3. Okay? Yeah, and now we introduce the additional labels for the optimized oracle. And we do this as follows. So for the B here we have this degree of 3, and therefore we have here B0. Doesn't matter which one is B0, which one is B1 and which one is B2. Just one has to be, some assignment has to be done. Okay, then here I remove the A. For the A there is only one successor, so we put a star here. This means we have A0, A1 and A2 here. Here is the same, we have A star here, here we have B star, here we have A star, and we have B star, and here is also only one A and one B successor, so we have A star and B star here. Here we have to be a bit careful. For A we have A star, but for the B we have 1, 2 successors, and now we have to use the modulo. So we have B0 here, we have B1 here, and then we have B2 here. Yeah, and now this automaton has alphabet A1, A2, and A3, and A0, and B0, B1, and B2. And obviously, when we just look at the transition relation, then we see it's now complete and also deterministic, except for the problem that we again have 2 initial states. Yeah, so this is how the variant with the optimization works, where we use numbers in order to encode the non-deterministic choice we have. With this, I want to conclude today's lecture, and next week we proceed with further topics on finite automata. Thank you very much for watching.